All right, so today let's continue on our journey learning about instantaneous rates of change, and we'll take a look and see what it really means graphically if when we're calculating or estimating an instantaneous rate of change. So we know an average rate of change. Again, we've been working on this for a long time, but let's get a formal definition down so that we can compare it to that of our instantaneous rate of change. So an average rate of change describes the rate at which a dependent variable, and that is y, increases or decreases over a specific interval. Okay, so we can call that in between x1 and x2. Graphically, it's the slope of the secant line connecting 2 points connecting 2 points on a function. Now we know the equation that we're working with. Again, we've been doing this for a few days now. Our average rate of change is the slope of our secant. That is given in function notation here. Now the instantaneous rate of change describes the rate of change of a dependent variable at a specific point. So we no longer need to specify over a specific interval, and that can help us to glean a little bit more detailed information. Graphically, it's the slope of a tangent line this time, not a secant. So a secant connects 2 points on a curve. A tangent line approaches and touches a curve, but does not cross a curve. Okay, so graphically, it's the slope of a tangent line touching a curve at a single point on our function. It can be estimated by using our difference quotient, and the difference quotient, hopefully we have a little bit of practice with now. That's our instantaneous rate of change. It equals the slope of the tangent, and that's approximately equal to the difference quotient, which really brings the difference quotient is an average rate of change, but it lets us estimate the instantaneous rate of change because the distance between our x1 and x2 is extremely small. In this case, we call it h, and often it's we'll use 0.01 or 0.001, something very, very small. Now for practice, we want to practice just sketching here our tangents. Okay, so we want to make sure you're using a straight edge if you've printed this off. A key part of working with a tangent is it must be a straight line. So we want to sketch a tangent line at 5 points along this curve. Whoops, I lost my tangent line there. When we do that, let's zoom in nice and large for you. And you know what? Actually, I'll say pause the video here. Try it out yourself. It's a line that touches but does not cross this curve. I want you to sketch it 5 times. Sketch 5 different tangent lines. So 5 tangent lines at 5 different points on here. Now they cannot cross the curve where they touch the curve. So where the tangent line comes into play, but they can cross the curve elsewhere. Okay, so if you're a little bit confused, you can, at the very least, watch me sketch one, and then you can draw them on your own. If you feel ready for it, then go for it already. So I might sketch, say, right here, I see an x-intercept at, looks like it's about negative 1.1 and 0. And if I sketch a tangent line here, it would look something like this, where it approaches the curve, does not cross, it touches the curve, so it touches that point there, and then it continues on without crossing. Now in this case, this does not cross the curve whatsoever. But let's say I take a tangent line on the other side here, at this intercept. I happen to choose intercepts here. You don't have to use intercepts at all. You can take them at any point. A tangent line at this intercept might look something like this, which we see does cross the curve down here, but we don't care about that. This is the part where it is tangent to the curve. Okay, that's what makes it a tangent. So I want you to come up with 5 different tangent lines here. I encourage you to try and come up with 5 different tangent lines that some are positive, some are negative, and some perhaps have a 0 slope. Okay, now the slope of a tangent that touches f at x equals a, it's our instantaneous rate of change at x equals a. So let's examine our function. This is a quadratic function with a transformation here. What transformation is it? I pause dramatically. It's a vertical translation 2 units up, right? I see a +2 over here. So it's we take our base quadratic function. I'm going to go a very rough sketch right here. we're looking at something like this. I just want the general shape here. General shape, and I have the symmetry. So I've sketched the function. That's what I'm looking for, where it has been translated 2 units up. And then I want to use the equation that I'm given up here, and or I can refer to my sketch to complete the table below. So in this table, what we're working to find is the slope of the secant between two points that are getting closer and closer together. So first, our 2 points are where x equals 1 and where x equals 3. Where x equals 1 here, and if I had sketched a little bit nicer, then it may have been useful. That's right here. Where x equals 3, that's much higher, right? So let's I can use my my equation to calculate here. I know my equation is f at x equals x squared plus 2. Okay, so where x2 equals 3, then f at x2 would equal 3 squared, that's 9, plus 2, that equals 11. The slope of our secant, again, you should be masters of this by now. The slope of our secant between x1 and x2 can be given by 11 minus 3, and this is the slope of the secant, given by 11 minus 9 divided by 3 minus 1, and that is 2 over 2, which equals, 11 minus, not 9, 11 minus 3 here. 11 minus 3 divided by 3 minus 1. So 11 minus 3, that is 8 divided by 2, and that equals 4. So the slope of this particular secant is 4 right here. And sorry, this is, we're expecting a secant kind of looking like, let's draw it in red here. Secant, again, remember, a secant as opposed to a tangent, it touches our curve twice. I'm looking at something along the lines of that, right? Where I'm touching the curve, and again, my curve is just rough, but where I'm touching the curve at those 2 points. So I want you to fill out the rest of this chart. And having done so, we can, I want you to compare your answers to mine right here. Having done so, we notice as x2 here gets closer and closer to x1, right? x1 is consistent throughout this. x1 equals 1. So we're approaching 1 from the right side, right, with values that are higher than 1. We start off at 3, we get closer and closer and closer and closer to 1. And as we get there, we can see that the slope of our secant, it begins at 4, but it gets closer and closer and closer and closer to 2. Okay, so here we say we're approaching the point 1, 3 from the left. Now, as we approach, and I'm just going to start filling out this summary a little bit out of order before getting to that to the next table. As we approach the point 1, 3, right? 3 is my y coordinate where x equals 1. As we approach the point 1, 3 from the left, the slope of the secant line approaches 2. And then we can try this as well from the right. I want you to fill out this table yourself. You can pause the video here. And where this time we are obviously we're creating the table on our own. So that means you need to find out. This time we'll keep x2 consistent as we work through, where x2 equals 1, and again we're filling it out on our own. So I'll pause, and we should be able to see here that as our x1 this time approaches 1, and you may have chosen different values here as we approach 1 from the right. And folks, I'm sorry. It looks like I confused myself a little bit here with our first table. So let's. I am going to leave this in because we all make mistakes. But our first table was approaching from the right, because our points x2 they're all greater than x1. This time we're approaching from the left. But this time when we do approach from the left, we see that the slope of our secant approaches, it gets closer and closer again to 2. Now we can say here that since the slope of the secant is approaching 2 from both sides, we can make a pretty definitive conclusion that the same is true when we approach from the right. They're both true. We can make a pretty substantial conclusion, a conclusion with a fair amount of confidence, that our rate of change is approximately 2 at the point 1, 3. Now, I'll say right now it is beyond the scope of this course, but when you get into calculus, then you will actually be able to calculate that exact slope there, and you will find that it is in fact exactly equal to 2. But we're not there yet, and that's okay. So we'll keep pushing forward. Now we notice here that each time our delta x, so that's our interval, right? Our delta x gets smaller. So the distance between x1 and x2 gets smaller each time. With our, as we got closer, it started off where the difference was 1, and then the distance was 0.5, and then the distance was 0.1, and then 0.01. So we're making our delta x get smaller and smaller. So the slope of our secant gets closer and closer to the slope of the tangent, right? It almost becomes a tangent, if you will. So as we, let's say we look at this this quadratic here, we began using the 2 points where x equals 1 and x equals 3, and then we got closer and closer and closer, and then eventually our 2 points are basically sitting on top of each other, and the secant that they create mimics. It's not actually, it's not actually a tangent, but it mimics that of a tangent. It starts acting like it's a tangent as those points get closer and closer. Okay, so that is as the delta x approaches 0, and that is as our interval approaches 0, then the slope of our secant approaches the slope of the tangent. So here we are, we're using that new notation, and hopefully we're able to follow it and connect our previous work there. Now still, if we're working with f of x equals x squared plus 2, we can use our difference quotient, which again we practiced yesterday, to estimate the instantaneous rate of change at x equals 1. So into our difference quotient here, again, you should be relatively comfortable with this. So I encourage you, pause it, try it out on your own, and then you're about to see the answer pop up in a moment here. And here we are, where we have substituted in our value where x equals 1 and h equals, again, we're using something pretty small here. I used 0.001 for h. And we substituted in. I did run out of space, so I had to come back up here. But either way, we're staying pretty consistent with as we work. Now, this gets a little bit ugly, and I suspect many of us find this not overly of an enjoyable experience. So we'll try and clean it up a little bit. What I encourage you to do is try and get a little bit more clever with your h here. I suggested equals 0.01, but we could, like I said, we can use 0.001 if you prefer. I encourage you to try substituting in h equals 0.01 elsewhere in the problem, so at a different step. Initially, I substituted it in here, but if you try substituting it in at a different point, see if you can make your solution come together a little bit nicer. Okay, so I encourage you to try that on your own. We'll talk about that in class. We'll compare how we were able to handle that in class. Next, I encourage you, once you're able to finish that, then you're ready to handle the practice problems. Again, we can get to these in class. I'm not going to go over every single one of them, but you will have time to do them in class. You should be able to handle each and every one of those right now. 3 is a nice practice problem in terms of getting ready for handling what will come next. Now, our instantaneous rate of change, again, here we're finding it by checking from the left and from the right. Right here, checking from the left and from the right, and seeing if if our slopes are approaching the same number. Here they were both approaching 2 from opposite sides. So that must kind of come together if we're going to evaluate or estimate an instantaneous rate of change. So a few requirements are needed if we're going to be able to consider an instantaneous rate of change. Number 1, in order to have an instantaneous rate of change at x equals a, our function must exist at x equals a. Okay, it must be defined, and that means that it cannot have a hole there. Okay, it cannot have a vertical asymptote there, and it must be part of the domain. A must be an element of the domain. Next, the function must be continuous at x equals a. That makes sense, right? We cannot estimate an instantaneous rate of change if our function is if we're lifting our pencil off the page and we're moving it an amount before putting it back down. At that point, our instantaneous rate of change would be positive or negative infinity. That's not very useful to us. So we won't be able to handle an instantaneous rate of change at a point where there's a break or a jump. Lastly, for an instantaneous rate of change to be true, if you will, the slope must be approaching the same value from the left as it is from the right. And that means that our slope cannot suddenly, shockingly change. And that is, if we're looking at example 1 right here, where x equals, and looks like it doesn't line up perfectly, but it should, where x equals 5 here, we see what we call a cusp. And this cusp, or a corner, occurs where the slope is, here it looks like it's going nearly infinitely, and I guess not infinitely, but it's very steeply positive, just to the left of where x equals 5. And then as we look just to the right of where x equals 5, I'll grab another color here, then I'm looking at a relatively strong negative slope. So the sudden shocking change here in slopes, as I have moved infinitesimally small amount here, that prevents us from calculating an instantaneous rate of change there. So a cusp or a corner will have no instantaneous rate of change. So where x equals 5 here, no instantaneous rate of change. Over here, I want you to take a look, consider where do you think, which x coordinates do you think we will not be able to calculate an instantaneous rate of change? And obviously over here, I've already talked about it, where there's a jump, then we're not able to calculate it where x equals 1. So I want you to try out this here, find the x coordinates where we're unable to find an instantaneous rate of change. Lastly, if you feel ready for it, then try it out on the graph below for all of a through h. Then I want you to state whether the instantaneous rate of change, and again, that is the slope of the tangent, would be positive, negative, or 0. Try it out. We'll compare those answers in class next time.